Good afternoon, everyone. So here today, we are blessed to have with us Sophie Aiken, who will be sharing insights about progress on the fractional Yamabe problem. Welcome, Sophie.
Thank you so much. Yes, so some people have already heard this talk, but I'll try to add parts in different places for the people who have already heard it once or twice. Okay. So the question sort of begins with the famous uniformization theorem in 1907, which said that every connected two-manifold is diffeomorphic to a quotient of one of these constant curvature model spaces, so either the flat plane or the sphere or the hyperbolic plane. And what this means for our context today is that every connected two-manifold has a complete Riemannian metric with constant Gaussian curvature. Okay. So this is a really interesting theorem sort of on its own because it connects the geometry and the topology of these spaces, right? It takes sort of questions that we could say about the topology of these spaces and allows us to make them sort of geometric questions by doing these classifications. So it'd be very interesting if you could do a similar classification for higher dimensional manifolds. And that's exactly what Yamabe asked in 1960. Given a compact Riemannian manifold of higher dimension, 3 or greater, can we find a metric conformal to the given one, which admits constant scalar curvature? Okay, and here conformal just means that we have a metric which gives us the same measure of angles as G does, but it might change our distance measures a little bit, or a lot. Okay, and so if I want to know that my metric, G tilde, which is conformal to the given one, admits constant scalar curvature, I need to know how this scalar curvature changes with a conformal transformation. So that's exactly what we have here. If phi is some conformal factor, it's just a positive smooth function that I multiply onto G. So phi to the 4 over n minus 2 times G gives me another conformal metric. Then the resulting metric G tilde has the following transformed scalar curvature. And we see that everything inside the parentheses here, this is what we're going to call the conformal Laplacian. And if we think about taking this sort of prefactor of phi, multiplying it to the other side, we get the Yamabe equation, where if my S tilde actually is constant, equal to some lambda, then I will satisfy this equation. So we want to notice real quick that the conformal Laplacian is so named because it's a conformally covariant operator. And this shows us how this operator changes with a change of conformal factor phi. And now we've reformulated this geometric question as an analytic question. So finding a metric G tilde, which admits constant scalar curvature, is the same thing as finding a conformal factor phi, which solves this PDE. Now, one way to solve a PDE is by using this technique of calculus of variations and the least action principle. So I want to find a functional which has my particular Yamabe equation as its Euler-Lagrange equation. And it turns out that this Yamabe functional here is the correct one. So we have sort of two formulations here. The first one, the very geometric formulation, where I'm just literally taking the integral of the curvature and then dividing by a volume. And then we have the same thing here where I can sort of fix a background metric G. In this case, it's my given metric from the Riemannian manifold, and consider the functional as taking in actually that conformal transformation. Okay, so now we see that solutions to our Euler-Lagrange equation, which is the Yamabe equation, are just critical points of this functional. So we're going to look specifically for minimizers of the functional, and call the Yamabe constant is infimum across the conformal class. So if we can realize the infimum, then we've found a minimizer, and we know that we have a solution. Okay, in general, it's not easy to know which conformal factor or which conformal metric actually realizes this infimum, but we do have an example here for the standard sphere, where across your conformal classes of the standard spherical metric, the standard spherical metric is actually the one which realizes the infimum, and we get that the Yamabe constant is equal to sort of this factor times the volume to a power. Okay, so going through sort of the steps of the original solution to this problem, the goal and what Yamabe tried to do was to find a minimizing sequence which will realize this infimum. And so you can see here that we're changing the norm on our denominator here, where in the original Yamabe functional, we have this norm with the power 2n over n minus 2. But we're going to allow sort of subcritical powers to create this sequence. And we say that if phi is a function which minimizes this subcritical problem, which is the same thing as satisfying our subcritical Yamabe equation, then we hope to take the limit of that sequence to get a solution to the actual Yamabe equation. But the problem here is that Yamabe claims that this sequence will be uniformly bounded, so the limit will actually be a true, like, non-trivial solution. But that's not the case, because as the name would suggest, we're calling this the critical exponent, because it's exactly the exponent where we fail to have compactness of the Sobolev embedding here. So just taking the limit of that sequence does not work to give us a non-trivial solution to the problem, or to guarantee a non-trivial solution. So to sort of overcome this, Yamabe, Schrödinger, and Aubin showed that you can work around this compactness issue as long as you know that the Yamabe constant of your given manifold is strictly less than that of the sphere. Okay, so if you're strictly less than the constant for the sphere, then you do have a solution, meaning you can find a conformal metric which admits constant scalar curvature. In addition, Aubin showed that we always have that the Yamabe constant of a given compact Riemannian manifold is less than or equal to that of a sphere. Okay. And so just sort of a brief outline here. He showed that by comparing the your metric G to the standard spherical metric, where this V sub L is just the stereographic projection with a dilation by L. And then I'm going to compare my given metric G by writing a conformal factor U delta, which is the stereographic projection times some bump function. And then when I go to write out the Yamabe functional of QG with this transformation, it's basically going to split U delta. I can decompose it as this bump function times the stereographic projection, and I'll get out just exactly my standard spherical Yamabe constant plus a little error. Okay. So at this point, if we know that the Yamabe constant is always less than or equal to that of the sphere, and in particular, the problem is solvable when we're strictly less than, we come to these next two questions sort of naturally. When do we have solvability from knowing that it's strictly less than the Yamabe constant of the sphere? And if I don't have that case, if the constants are actually equal, is there some other way to prove solvability? So Aubin started to answer the first question by saying that if M has higher dimension, 6 or greater, and it's not locally conformally flat, then we get this criteria of strict inequality. And Shane rounded it out by saying, okay, in these other dimensions, 3, 4, or 5, or if M is locally conformally flat, then we still have the strict inequality. The only time when you don't have that is if M is actually conformal to the standard sphere. But that's okay, because if we're conformal to the standard sphere, right, then you know that you have a conformal metric which admits constant scalar curvature. Okay. So that finishes out the solution to the classical Yamabe problem. And now we want to talk a little bit about formulating a fractional version. Okay. So a bit of geometric background to sort of set the stage for the problem. I still want to be considering as like my main Riemannian manifold of interest, this M, but I now want to consider it as the boundary of some higher dimensional manifold, okay? So X is going to be the interior or like the filling in of this boundary M. And we'll walk through these definitions with an example case as well. So we can imagine here that I'm given this manifold. Yes, okay. So we're given sort of as our xn plus 1, the Poincare disk model of hyperbolic space. So just our two-dimensional disk with the hyperbolic metric. And now we'll define rho as being a defining function of the boundary if rho is a strictly positive function on the interior and it's exactly equal to 0 on the boundary, and the differential is non-zero on the boundary. So it's called a defining function because this level set when rho is equal to 0 exactly defines our boundary M. Okay, and now we can sort of notice, we can pick out a defining function in our definition of the hyperbolic metric by seeing that the hyperbolic metric is exactly your Euclidean metric divided by some squared function. So we've multiplied that to the other side. I have my defining function times the hyperbolic equals Euclidean. This defining function is just a special case of a conformal transformation as well. So this is showing the conformal change between Euclidean space and hyperbolic, or the Euclidean metric and the hyperbolic metric. Okay. So now, given my interior xn plus 1 with a metric g plus, I'll say that this manifold is conformally compact if for any defining function, multiplying my given metric g plus by rho squared creates a new metric g bar, which now extends to the boundary such that the closure of xn plus 1 with this g bar is now a compact metric. So that's why it's called the conformally compact. This defining function is allowing us to like compactify here. Okay, just a bit of notation. If I now take g bar, so this extension of g plus, and restrict only to the boundary, I'm going to call that g hat. Okay. And since we had in our definition of conformally compact, I want this to be true for any defining function. That means that I have actually a whole class of conformal metrics on the boundary based on those various choices of what the defining function could be. So now if I look at my boundary M with the entire class of conformal metrics, that defines our conformal infinity. And returning to our example here, we see that our ball with the hyperbolic metric is conformally compact, with the conformal infinity being exactly that boundary S1 and the conformal class of all Euclidean, everything conformal to the Euclidean metric. Okay. One more definition we need. We're always going to consider our interiors, these n plus 1s, to be asymptotically hyperbolic Einstein manifolds. So Einstein for us just means that the Ricci curvature is equal to this constant times the metric. So particularly, we want to normalize so that it's negative n times the metric, where n is the dimension of the boundary. And asymptotically hyperbolic means that the manifold is asymptotically locally hyperbolic. So as I approach that boundary, the sectional curvature approaches -1, that hyperbolic sectional curvature. Okay. So given a conformal Einstein manifold, for each representative of my conformal class, so picking out a specific metric in that conformal class, associated to it is a unique geodesic defining function, so a special type of defining function, such that I can expand my inside metric g plus in this normal form. Okay, and we need this special geodesic defining function to define our scattering operator. So we had sort of our geometric background, and now in order to define the fractional Yamabe problem, we need a fractional equivalent to the conformal Laplacian, and that's what we're going to get here with the scattering operator. Yeah. It's a sort of what?
What do you need that is?
Yes, so the x is a special kind of defining function, which basically allows you to have this normal form extension. It measures the distance from the boundary, right? So it's 0 on the boundary and measures positively inward. And so we get this expansion of G plus, and each of the sort of G sub x's themselves has an asymptotic expansion, which I didn't want to include because it's kind of gross, but is important for getting the estimates later on. X equals 0. Yeah. Okay. And so now we can consider any smooth function f on my boundary, little f, and define this Poisson equation. So I have the negative Laplacian just with respect to my G plus metric on the interior, and this boundary condition that capital F equals our given little f, and this capital F is showing up in the expansion of our solution U. And we need geodesic out the expansion of that solution. Oops. Okay, so now if we look at the other half of the expansion, capital G, and restrict back to the boundary, that's equal to some operator acting on my f restricted back to the boundary, which is really just little f. And this operator, scattering operator, for our purposes, we want to normalize, okay. So we'll use the regularized scattering operator instead of just straight scattering operator S of n over 2 plus gamma, because now we have a conformally covariant operator again, which is really what we want. Yeah. I know I got two when it skipped and I had to go back. Yes, so gamma is our fractional constant. It can be anything greater than 0. For defining the problem, it can be anything greater than 0 with caveats. So it has to sort of avoid the spectrum of your Laplacian. Otherwise, it's not defined here. For today's talk, gamma is always going to be between 0 and 1 exclusive, but you can define higher order things for sure. Yes. Oh, see, it skips. Okay. Okay. Sorry, can you repeat that? So any solution here should have such an expansion, you mean? Gamma is fixed. Yes. Yes, you can define the problem for multiple gammas, but once you, in order to define this, you fix a single gamma. Yeah. Yes. Mm-hmm. No, I last time I double clicked and then it skipped. So I clicked once and now I'm waiting, but I don't think it.
So if gamma is 0, you keep the spectrum of the Laplacian? That's what you mean.
Yes, so if gamma is 0, well, but also there could be a discrete spectrum, right, between 0 and n squared over 4. And so you need to avoid those values as well. Yeah. Okay, there we go. For us, since we're using the yes, this is, we'll get to it in a second. I'll wait until it comes up in the slides. Okay. So now that we have our operator defined here, the regularized scattering operator. But we can notice for a second to sort of maybe frame ourselves a little bit. If we fix certain gammas, we'll recover more familiar operators, right? So if I fix gamma equals to 1, we recover exactly the conformal function from the classic Yamabe problem. If you fix gamma equal to 2, recover the Panites operator and sort of your fourth order Q curvature problem. All of these integer values of gamma, you'll recover the series of GJMS operators. Okay. So now we can define our fractional order curvature, the thing that we're trying to make constant, just by seeing how our regular scattering operator acts on the constant function. And this is exactly the way you can sort of recover your scalar curvature using the regular conformal Laplacian as well. Okay. And now we can define our functional, the normalized total curvature, in the same way by taking the integral of our fractional curvature and dividing by the correct volume. Okay. So now that we've defined all of our pieces, we can formalize our fractional Yamabe problem, which is to say, is there a metric in this class which admits constant, now fractional curvature, which is the same thing as saying we minimize our total curvature, the functional. And again, our fractional Yamabe constant is exactly the infimum of that functional that we're trying to realize. Okay, so some previous progress that has been made on this problem. Again, we know that the fractional Yamabe constant of this sphere is actually achieved by your standard round metric, and is equal to, again, sort of a constant times the volume to a correct power, or it was just 2 over n, now it's 2 gamma over n. This first is also from the same paper by Gonzalez and Ching, but it's just sort of a remark in there. Anyway. So now if we have our interior xn plus 1 g plus being, for our purposes, an asymptotically hyperbolic Einstein manifold and gamma between 0 and 1, then we always have that the fractional Yamabe constant is less than or equal to that of the sphere. And also, we have the same thing. If your fractional Yamabe constant is strictly less than that of the sphere, then the problem is solvable. And just as a note, these two results from Gonzalez and Ching are actually a little bit broader. They don't need the interior manifold to be Einstein. It's just asymptotically hyperbolic with a Ricci lower bound condition. Okay. So now going forward, we want a way to handle, as before, the case when this fractional Yamabe constant is actually equal to that of the sphere. So we're going to tackle this from a rigidity point of view, where we have this question: if I have an asymptotically hyperbolic Einstein manifold as my filling in, and I know that my boundary is already conformally equivalent to the sphere, does that require that my interior be isometric to the hyperbolic space? So does knowing something about the boundary require rigidity of what the interior actually is? So again, same setup. I have my boundary as a complete Riemannian manifold. And now we're just using this Ricci lower bound condition. We're going to review sort of the classic Bishop relative volume comparison, which says that I have this quotient of my volumes of geodesic spheres, where here I have my geodesic sphere in interior metric G plus, and then on the bottom, I have the geodesic sphere of my hyperbolic space. This quotient is always going to be less than or equal to relative volumes of the geodesic balls, which is always less than or equal to 1. And also, I have that both of these quotients are non-increasing functions of t, where t is just a distance function on these manifolds, okay? So t is approaching infinity as you go out to the boundary, and 0 at some like fixed point on the interior of the manifold. Also have that if somehow the volumes of my geodesic balls are equal, then that does imply that my interior is actually isometric to the hyperbolic space. Okay. So sort of a natural question just arising from this side, is there a lower bound? So you have this very classic geometric volume comparison with an upper bound. Is there a way to put a lower bound on this? That's an interesting question sort of on its own, but also for us, we want to ask this rigidity question, which means I want some way to force equality of my geodesic balls, which means I kind of want to force a lower bound here that is going to be 1 in certain cases. Okay. So this process of finding a lower bound, the first thing we want to do is understand how geodesic spheres with large radius compare to sort of level sets of our defining function. Right, so geodesic spheres are working with distance functions moving sort of out toward the boundary. Our functions start at 0 on the boundary and push in. So I need to know how these two sort of spheres line up. Do they compare well? It turns out if we force our interior to be an asymptotically hyperbolic Einstein manifold, then geodesic spheres are pretty similar to actual round spheres, which is good. So it's going to sort of play nicely with the level sets of the defining function. And that's the main idea, is to understand the relationship between these two distances, building from the interior out and from the boundary in. Okay. And so that's the sort of form of steps that Liching and Xi followed to show that you can get a lower bound as a quotient of your Yamabe constants. And this, I think, is really interesting on its own, because you're taking something, you're saying information about the interior of your manifold only using information about the boundary. And this result actually answers a question sort of even broader than the rigidity theorem, which says that if I only know that my Yamabe constants are equal, so not that the boundaries themselves are conformally equivalent, just that the constants are equal, then I get an isometry between the interiors. Okay. So going through, again, sort of we've talked about this rigidity statement and how we're going to use it in terms of the classical case. We're going to finish that out. Recalling the original work of Yamabe, Schrödinger, and Aubin, we have always that the Yamabe constant is strictly less than that of the sphere, and it's solvable, or sorry, it's less than or equal to, and it's solvable if you're strictly less than. And now instead of using sort of the major machinery of the positive mass theorem, we can, in this particular scenario, answer what happens when we have equality by using the previous result of Liching and Xi. So if I have my boundary of positive Yamabe type, just means that the Yamabe constant is positive. But for us, we're going to assume that it's equal to the sphere, so that's no restriction. Then we get that our boundary is actually conformally equivalent to the sphere, and the interiors are isometric. Okay, so this is a way to sort of finish proving the Yamabe problem without using this massive machinery of the positive mass theorem that kind of happened to apply here. You know, this is a much more direct way to finish that out. So the goal would be to do a similar thing in the fractional Yamabe case. And it turns out that Wang and Zhu were able to prove a similar lower bound using the fractional Yamabe constants. And they actually claim that this is a slightly improved lower bound, fitting a little bit more snugly than the classic Yamabe constants in the case when gamma is 1/2. Okay, and so a brief outline of their proof for showing this lower bound. They want to reformulate the normalized total curvature in sort of a more useful way this time. So rather than defining the scattering operator and the regularized scattering operator using the Poisson equation, they're going to use a different boundary value problem. Okay, and by doing that, I get sort of a different numerator in my total curvature functional. And it's important to get that different numerator because now I have something that I can more easily compare with these volume comparisons. Okay, and then once I have this volume comparison, I'm going to sort of use limits and conformal factors to move to what I really want, which is the relative volume of these geodesic balls or geodesic spheres. And here this tilde and the G sub infinity, this is like where Wang and Zhu made a really smart choice of which metric within these conformal classes would be sort of the right one to use to compare to the upper bound. Okay, here we go. So like I said, we want to find our operator, not using the Poisson equation, but using this boundary value problem here, where my E of rho is defined as follows. And the reason we want to do this reformulation is because I can choose a specific, this rho is a defining function. So I can choose a specific defining function within my class, which they're calling this adapted boundary defining function. And it's an important choice because you have this asymptotic expansion where the curvature shows up. So you want that the fractional curvature shows up sort of already inside of your functional. Okay. So as I mentioned, right, sort of built into this functional now, I have a term which also includes my fractional curvature. Yes. And so knowing from the previous results of Gonzalez and Ching what this fractional Yamabe constant actually evaluates to, we can sort of rearrange this to be exactly showing that just the numerator of my functional, which already includes the fractional Yamabe, the fractional curvature by the reformulation step 1. Now I just want to show that that's equal time curvature. Okay. Great. So maybe put too much technical stuff on the slide, but the gist is to my comparison of geodesic spheres to recover sort of our classic Gromov-Bishop volume comparison. And the way I do is by they made this special choice of a conformal factor, where T really is this distance function going out. And then they're able to sort of rewrite what your background metric is and then use like dominated convergence theorem to deal with the limit. And then finally, just by Gromov-Bishop, we know that this quotient is always a non-increasing function. So I can pick a bound by fixing a specific time or a specific distance t. Okay. So once you have that lower bound, now we can say that if the fractional Yamabe constants are equal, that lower bound is 1, which forces equality of my relative volumes, meaning that my boundary is actually conformally equivalent to the sphere. And so just putting that together with the two previous results of Ching and Gonzalez, you've covered sort of all the cases of your Yamabe problem. So for this special scenario where we have gamma small between 0 and 1, the fractional Yamabe problem will be solvable. Again, you could do it with higher gammas as well, but I haven't thought at all about that. So that's all for today. Fine.
Thank you, Sophie, for the interesting. Are there questions?
You define this conformal Laplacian.
Mhm.
It looks like eigenvalue problem, right?
Hmm.
So,
Mhm.
so I wonder, could it be studied from that point of view of an eigenvalue theory? And if so, what would you mean to have a resonance in like an eigenvalue theory?
Can you say that last part? I don't know what a resonance phenomenon is.
The lambda equals an eigenvalue theory.
Oh, okay. I don't know. So I think well, I don't know. I haven't thought about it at all for like the classical conformal Laplacian, but I know when sort of defining the scattering operator in the original work of like Graham and Zworsky, it's very much from an eigenvalue problem perspective. So I don't know much more than that, but that's where I would look. Yeah. Mhm.
One conformal, one shape of boundary, or
Hmm. Yeah, that does make sense. I've always sort of thought about it the other way around, right? If you have one boundary, you have sort of multiple possible interiors, and so you want to fix, in this case, say it again?
no, no. If you can choose a good one.
Right. Well, yeah, if you fix. I'll think about it.
You look the value of the here, right? When you don't have contact with it, you have to be interested in sharing. Like, we can construct multiple solutions, especially inside the environment. We have to get something that's interesting.
Okay.
Do you feel that that kind of thing can be done? Yeah,
Do I feel it?
we need to tell the bank that to take the bank. We go to the
Can you say it again though? Like yes, if you have, you're realizing the sphere, then in the classical case, you did in the classical case, if you have the sort of critical exponent and you're realizing the sphere, then
Yeah.
right.
I don't know. The spectrum settings are very, everybody is having settings. You get to define.
Mhm.
It's very in the
Yeah.
You mentioned the reverse change result, the first one.
Yeah.
They didn't use for asymptotic and hyperbolic again. They only assume the big over that.
Yeah.
So, but in this study, there is some hope because you're assuming the
Yes.
hope for
The Ricci lower bound. I mean, I think not using the same proof method as what long as you already have. You sort of, yeah.
actually don't see the classical platform.
Or something else, yeah.
Is there any sort of study?
Not that I know of. But
Because I know, I mean, there's not this big problem that they were using for the
positive nothing for 430. Who was that?
what's the student? Yeah, the
Mm. Thank you. Yeah.
Sorry. Okay, again.
okay, thank you again for
Before we go, we have some information. The first thing is that we are celebrating today the seminar number 30. The middle of the semester, we are back today. And today is officially the last of my last participation. And thank you very much. Three women work in the seminar.